If you search YouTube for DIY magnetic vices, chucks, bases, or whatever you want to call them, you will only find them based on electromagnetism. Large, plumb blocks of metal with heavy electromagnets. No constructions a hobby instrument maker can get excited about. Apparently making a slim magnetic chuck based on permanent magnets is very difficult. Indeed, stacking of magnetic and non-magnetic layers, pressing, welding sides, straightening, smoothing, brazing, milling, grinding, sealing with epoxy, pouring the base, and many more operations. Here are some shots from an instructive YouTube video.
What's our and what the process is?
Well, Don, we start with the pieces for our top plate. We've got our 2 end poles, we've got our non-magnetic stainless poles, and we've got our mild steel transfer poles.
Anyway.
Well, the stainless gives you the separator between your north and south pole, and that's what gives you your holding power. All of the gaps have to be filled with copper, and the copper is what holds this whole assembly together.
Once it's copper brazed, then what?
Once it's copper brazed, we have to take this blank and we blanchard grind it, all 6 sides, to remove the weld so that we have a nice clean edge on there. So now we've got our top plates done. They're all blanched, we know where the poles are. We have to start building our magnet box, which is laminated of mild steel and permanent ceramic magnets. When you put these magnets in there, they have to be put in north, south, so the best shut off, and we get the best holding power that we can attain. So after we've assembled all that, we pot it with epoxy, and then we blanchard grind the top so that we've got a nice, smooth, flat surface.
The holding power per square inch, what are we looking at? Any ideas to...
These standard pole like this averages about 35 pounds per square inch.
But still, is it really not possible to make such a permanent magnetic chuck yourself? Here's a run-up to the construction of such a device, in the form of a half-finished mini prototype. Enjoy! In some materials like brass and aluminium, a magnetic field doesn't travel easily, and some other, like steel and iron, allow a magnetic field to move with great ease. Clever use of this property, which is called magnetic permeability, enables us to create a magnetic vise that can be switched on and off. The global operation of such a magnetic base is explained in this sketch. All the green is air, or aluminium, or any other low permeable material. On the left you can see the vise in the off position. The steel columns overlap the plus and minus pole of the neighbors below. And, with their high permeability, they offer the magnetic field a path of least resistance, below the steel plate at the top. The steel plate will hardly be attracted. On the right, the steel columns are shifted to the right so much that they each touch a single pole. Again, the field chooses the path of least resistance, up through the steel, through the top plate and back again. The top plate is now strongly pulled downwards. One of the first things I need to figure out is what magnetic forces I can count on, and what the magnetic range will be. Intuitively I would say that the shape of the magnets is important. Thin flat discs or slender long bars seem less suitable shapes to me if I visualize the field lines. I expect the compact magnets like balls and short cylinders to be more powerful and to have more range. We will test that here first. 4 differently shaped magnets are clamped and pull on a piece of steel lying on a scale. By adjusting the height of the head of my mill, I can determine the pulling force within fractions of millimeters between the steel and the magnet. Here are the results of the measurements in a graph. My suspicion is confirmed. The most favorable shape is the sphere, which has lost half its tensile force at a distance of 850 microns. With the slender stick, this is already the case after 400 microns. The ratio of magnet volume and tensile force is with around 3 kg per cubic centimeter, also the most favorable for the sphere and cylinder. This is important because the price of the magnets almost only depends on their volume. Spherical magnets are not practical in this setup, but compact short cylinders seem to be a good choice. Since this is a prototype, the dimensions don't matter that much. I happen to have small neodymium magnets and some aluminum with which I can build some concepts and do small tests. An important difference compared to the usual models is that I will not stack, weld or glue a laminated base of different metal plates. I'm going to perforate aluminium plates, and press tiny neodymium magnets and steel cylinders into the holes. That's much easier to make, and it might work just as well. Of course that will be tested later on. The bottom is also of an unusual design. It will be exactly the same perforated plate as on the top. So the force between this magnetic vise and the table of the mill or grinder can be switched on and off. No bolting or clamping down needed. The magnetic vise pulls itself to the steel table of my machine, or any steel surface for that matter. An advantage of this construction is that the vise has little height and can be attached independently of T-slots. I can also use it for other purposes, like fixating steel in a certain position, or as an aid for my steel surface plate. The small magnets have a diameter of 5 mm and are spaced 1.5 mm apart. So if I move the intermediate plate with the magnets 3.25 mm, the steel rods should short-circuit all poles and there should be almost no pulling force left. And that indeed appears to be the case. It looks really good so far. And now I can start some small tests. For this I made a test setup from some rubbish and a small drill column, in which the scale that I made for my hardness tester serves as a measuring instrument. First I measure the pull force of the small magnets without the top plate. The steel test blocks have a surface of 3.28 square centimeters, and the force with which I pull it loose turns out to be around 7 kg. That is about 2.1 kg per square centimeter. 35 pounds per square inch, as Suburban Tools quotes in the video, at 800, equates to 2.46 kg per square centimeter. But with these mini magnets I'm already pretty close to that, which is encouraging. Now let's test how much tension loss I get when I put the top plate with the 21 steel cylinders between the magnets and test block. That is very surprising. More than 70% more, about 12 kilograms, which amounts to 3.66 kilograms per square centimeter. This is almost 50% more than what was mentioned in the video. Very encouraging. I do wonder what the physics is behind this large and unexpected difference. I don't have a good explanation for it at the moment. If you think you know the answer, I'd love to see it in the comments. Another concern is friction. The plate with magnets is firmly sandwiched between the top and bottom plate, and it will take quite some force to slide it between them. I'm testing that right here, and approximately 2.8 kilograms of shear force is needed when using one plate only, so totaling 5.6 kilograms for both. That is roughly 45% of the 12 kilograms holding power. That is a cause for concern. How are the surfaces of steel and aluminum affected by the repeated sliding and this high friction? Dry sliding can certainly cause a lot of wear in the long run, but a layer of grease or graphite does not seem to me to be the best solution. I'm thinking of a layer of Teflon as lubricant, and that is what I'm trying out here. Just a very thin layer of PTFE tape. That makes a lot of difference. Now the required shear force is only 0.8 kilograms, which is about 1.6 kilograms in total. 15% friction now, compared to the 45% without the tape, is promising. But how long will such a thin layer of Teflon do its job? Here too, I put together a test setup of some rubbish and a reduced electric motor for an endurance test. The magnetic plate is moved back and forth every 6 seconds, 24 hours in a row. That amounts to 14,400 opening and closing times. Since I will be using a magnetic chuck only a few times a week, this equates to decades of field use. The wear appears to be very limited. The thin soft Teflon tape has worn through in 1 or 2 spots, but it still does its job. The energy consumption of the test motor is the same as at the start 24 hours ago, indicating that the friction has not changed. The aluminum, steel and magnets show no visible wear. I think I now have enough information to start building a working magnetic chuck. Meanwhile, 250 small cylindrical magnets have arrived. The quality is fortunately higher than the small ones I used in this project. However, I will measure the height of each magnet to make sure that there is not one that will stick out. But that's for next time. First I have to pre-drill, re-drill and ream 750 holes. I'm really looking forward to that. See you then.